Welcome to Calculus. Thanks for joining for this second half of our Evaluate Limits graphically. Let's take a look at two examples to finalize our 4-example set for this session. So let's head back to our notes screen. And we looked at two limits up till now. So one of them had an evaluatable limit, the other did not. It did not exist. So let's see two more examples and see if we can find the limits for these functions. So our first of these latter two examples is limit as x approaches 1 of the function 2x plus absolute value of 4x minus 4. We'll start the same way that we've been working. We're going to begin by considering this as a function f of x equals 2x plus absolute value 4x minus 4. And I want to graph that. And I also want to look at the table. So in fact, we'll really consider that opposite. I'm going to create the table and use that to graph a sketch of this function. And then what we'll do is we'll make a more defined graph or a more defined table in order to evaluate the limit by a table. So let's take our traditional x values. And in fact, what I want to do is I want to center around this value at 1. So let's put 1 here. And then let's get a couple values on each side. So I'm going to back up to 0 and -1 on the left of 1, and then zoom forward to 2 and 3 on the right of 1. Now let's get our values. In fact, for this one, let's head over to the calculator to just reiterate that as one of the tools in our wheelhouse. So I'm going to head to desmos.com. And just like we wrote that function, I'm going to type it in. F of x equals 2x plus, and then absolute value. We had used the typing command before. I want to show you another way that you can find that here on Desmos. So here in the lower left, you can show the keypad, and then this upper right button, if I select that functions key and head over to the right column, miscellaneous, I can find the absolute value function somewhere. Well, I'm doing all that, and then I see actually it's right here on the main screen. So as you get more and more expert at this, you'll know where these functions are. And in fact, it's right here. So it's on the main keypad. Let's type in 4x minus 4. So notice that gives us actually the bars. And that's equivalent to that prefix ABS. So we see the function here, and it looks like an absolute value function graph, but the left-hand side is much steeper tilt than the right-hand side. It looks like a off-sided V. And let's take a look at our table. So I'm going to select that cog and convert to table for this function. And we had selected the value of our limit. So we looked at 1. So I'm going to also supply a 3 there. And definitely these values support this idea of a V. So to the left of 1, these values are climbing down by 2. So from 8 to 6 to 4 to 2. And then they climb up much steeper from 2 to 8, 8 to 14. So they're going up by 6s. So I'm going to record that table. And at this point, let's write that down, and then we can create our graph. So -1, I believe we had used at 6, 0 at 4, 1 was at 2, 2 is at 8, 3 at 14. And let's head back to graph that on our notes screen. So we'll finish supplying these points. So -1 again was 6, 0 was 4, 1 was 2, and then 2 jumped up to 6. I'm sorry, let me back up to 8, and then from 8 we jumped up to 14. So let's plot those points. So -1 is up at 6. 0 is up 4. 1 is up 2. So definitely that's a linear function on that left side. And then at 2, we jump all the way to 8. So I'll go ahead and plot that. But at 3, 14 is off my graph. So I'm just going to leave it right there. So we've got this kind of tilted over V shape. So just to keep in view, what we're asking is as x gets close to 1, we want to know what is happening to the y value. So really 1 is here in terms of x. So we're saying what's the y value as we get close to 1 from the left and from the right? Well, direct substitution would actually work for this question. If I were to substitute in that value of 1, we could just plug it into this function as is. And when we would evaluate, we'd get 2 plus absolute value of 4 times 1 is 4, minus 4 is 0. So 2 plus absolute value of 0 is 2 plus 0, which is just 2. So we could actually calculate that one directly. The graph supports that, as does the table. So if I look at the graph at 1, that if I trace over the y-axis, that y value is 2. So we'll create this horizontal table, but really we kind of have an idea about the fact that it's working without us having to do all that. But let's see what it looks like. So 0.999 and 0.99. 1.001 and 1.01. So we do know that this is 2. Let's confirm in this more condensed table that the left and the right-hand sides are both reaching 2. So just to see that in place, let's head back to our Desmos screen real quick, and I'm going to exit out of that table and real quickly create a blank table. And we're going to put 1 there in the center. And then we want 0.999 and 0.99. And on the right, 1.001. Let me not get ahead of myself. No, that was correct. 1.001 and 1.01. All right. So what we see there supports this idea that the function, as we approach from the left of 1, is in fact getting closer and closer to 2. At 0.99, it's 2.02. At 0.999, it's getting even closer, 2.002. That gets right to that value at 1 of 2, and then at 1.001, it goes to 2.006, which again is very close to 2, and 1.01, 2.06. Well, let's record that table and finalize this limit. So we had found that these were real close to 2, 2.002, 2.02, 2.006, 2.06. So definitely the left-hand side is approaching 2, as is the right side. And we can finalize our answer here real carefully. So the limit as x approaches 1 for the function 2x plus the absolute value of 4x minus 4 equals 2. And I'll box that answer equation. Let's take a look at one final function. So this function it looks a little bit like absolute value, but let's read it. So we're interested in the limit as x approaches 2 of the floor function. So the name of this function is the floor function which is also known as the greatest integer function. I'm going to write in here in parentheses what greatest integer refers to. So when we look at the function and evaluate, it's going to be the greatest integer inside those little L-type brackets, less than or equal to it's the greatest integer less than or equal to the function. And by function, I mean that's that part of the value that's inside the brackets. We'll fill that in a moment. But let's get started with our table and our graph. So let's graph this function. And there's a lot of pieces to a floor function. So what I want to do is I want to kind of modify my domain so that I'm not using just integer values, but using some decimals in between the integers. So the ones that I want to choose are, let's go from 0 to 0.5 to 1, 1.5. And then our limit value is at 2. So I'm kind of interested what's happening around 2. So 2, 2.5, 3, and 3.5. I think that's enough for us to see what's happening there. So this one, let's practice evaluating this by hand. So I want to evaluate f at 0. And I'm going to pick up that greatest integer or floor function. And I'm substituting 0 for x, so 0 plus 1. So at this point, we're going to use this idea of it's the greatest integer less than the function. So our function value there simplified to 1. So we got to ask ourselves, what's the greatest integer that's less than or equal to 1? What's the greatest integer less than or equal to 1? Well, 1 itself. So this equals 1. Now let's see what happens when we've got a decimal. So we'll bump over here to f at 0.5. So we're looking at the floor function of 0.5 plus 1, which is the floor function of 1.5. So this is going to be a little more illuminating in terms of how does it work for decimals. What is the greatest integer that's less than or equal to 1.5? Still 1. 1 is the closest integer that's less than or equal to 1.5. Why isn't it 2? Good. 2 is not less than 1.5. It's greater than. So there's another function called the ceiling function that would give us an output of 2 there. But for the floor function, we're saying what's the greatest integer less than or equal to that number? So f at 1 is floor function of 1 plus 1, which is floor function of 2. And the greatest integer that's less than or equal to 2 is 2. See if you can predict f at 1.5 as we write this. So floor function of 1.5 plus 1 is the floor function of 2.5. And the greatest integer that's less than or equal to 2.5 is 2. So we can start seeing a pattern here. F at 2 is going to be floor function 2 plus 1, which is floor function of 3. And the greatest integer less than or equal to 3 is 3. F at 2.5 is 2.5 within the floor function plus 1 is 3.5. And the greatest integer less than or equal to 3.5 has got to be 3. And these last two, from the patterning that we see here, we got a 1, a 1, a 2, a 2, a 3, a 3. So this is going to be a 4. And f at 3.5 is also going to be 4. So let's graph these values and see how it works. So at 0, my value is 1. At 0.5, my value is 1. At 1, my value is 2. At 1.5, my value is also 2, but at 3, f at 3, I'm sorry, let me catch that. That's not f at 3. This is f at 1, 1.5, f at 2 is 3. I was saying the y value. At 2.5, the value is also at 3. At 3, the value is 4. And the same at 3.5. Now, we got to think in terms of, here's the framework. We've got these coordinate points. What's the actual graph look like? So definitely we've got a firm left endpoint. But here at 1, we have an open endpoint because the actual value of the function bumps up to 2. And we see that this is happening all along these segments. With the floor function, the left-hand side is a closed point, which means the function equals that value, and it corresponds to the piece below it. And if I were to continue this over on the left, we'd see a lot of these little segments. And that would go forever. So I'm not sketching the whole graph, but you get a feeling for what the floor function looks like. Another name for this, if you kind of look at the graph, it looks like a lot of steps. It's also called a step function. And a lot of real-world application for floor functions, for step functions. Now, what we need to determine, what's the limit as x gets closer and closer to 2? So I'm going to find 2. Remember, we went by halves here. So 2 is here. So we're looking from the left and from the right. And let's confirm what we're going to say here with our limit evaluation with that condensed table. So we kind of see what the function looks like, and you can kind of at this point make a hypothesis. Does that function exist? Is there a number that's the same as we come to the left towards 2 and from the right towards 2? But let's see. So 2, 1.999, 1.99, 2.001 there on the right, and 2.01. So I'm going to bump over to the calculator just to show you where the floor function is listed there, and we'll create this table there. So I've got to clear out these 2 previous inputs, and let's put in this floor function. So f of x equals, and then from the keypad, we do want to go to the functions key for this one, to miscellaneous. Kind of in the center of that catalog there is floor function. And ours is x plus 1. So notice it doesn't give you those L brackets, it just says the word floor. But that shows up real well and kind of confirms what we were doing with our graphs. So we got a lot of these steps. Now to see what's going on around 2, let's create a table. And I'm going to put 2 here in the center, and then let's go with 1.999 and 1.99 and 2.01, 001, and then 2.01. So what we see is that to the left of 2, that the values for this function are 2. So that's on this step right here. If you see here, I'm trying to animate on the graph itself. When I reach 2 itself, I bump up to the next step, and the output, which we can see in our table, is 3 all the way to the right until I get to 3, and then it bumps up. So let's record that, and then we'll make a final answer for our evaluation of this limit. So definitely as we look at these outputs, 2 and 2, and then 3, 3, 3. And so what I see is that on the left, as we approach the x value of 2, the y values are 2. Whereas on the right, as I approach the x value 2 from the right, the outputs are 3. How would you say we should answer this limit? The limit, again, we're going to write real carefully. As x approaches 2 of the floor function of x plus 1, is it 2? Is it 3? Or does it not exist? Good. It does not exist. And again, we want to put a reason for why this limit does not exist. So again, let's write it mathematically. The limit as x approaches 2 from the left equals 2. Those were these values that we saw there. Does not equal 3, which is the limit as x approaches 2 from the right. So again, that upper superscript of negative, superscript positive just means it's coming from the left, coming from the right. If those don't equal each other, we got to make the claim that that limit does not exist. Thank you for joining for these last two examples for evaluating limits graphically. See you next time.